Hello, everybody. Welcome to lesson one or topic one, which is on the production of power from heat. So just to acknowledge this, the original slides is from Professor Myra Borines. For our learning objectives or learning outcomes, number one, um, to qualitatively describe the idealized Carnot, Rankine, Otto diesel, and Brayton cycles and sketch each of them on a pressure volume or temperature entropy diagram. Number two, analyze an air standard Otto cycle or diesel cycle for a given compression ratio. Number three, compute efficiency and heat and workflows for an air standard Brayton cycle for a given combustion temperature and compressor and turbine efficiencies. Number four, explain in simple terms how jet and rocket engines generate thrust. We begin with um, overview of the global energy demand and energy sources. So here, this figure shows the global energy demand historically and the projection, future projection. So what's the general trend of the energy demand? It's increasing. So the main reason why we demand more energy, of course, because of the increasing population and also because of the lifestyle changes. Um, so today we use more and more, we travel more, we use more transportation, and we also use more appliances and gadgets. And also, say we use the elevator more than using the stairs. So all of this compounded demand results to a general increasing trend in the global energy demand. So how do we meet this demand in order to sustain our lifestyle? So we have to produce more energy. So we have to have more energy supply. And in order to have more energy supply or yeah, more electricity supply, we have to have more energy sources. Um, so in Earth, the sun is the main source of energy aside from nuclear power. So, how, what's the reason? Say, for example, for fossil fuels, which is the first source of energy that I'll be discussing, these are the result of the fossilization process of living tissues. And these living tissues came from plants and animals, where the animals ate the plants or other animals, and where the plants um, were able to grow because of photosynthesis and using solar energy. So that's why I'm able to say that the sun is the ultimate energy source here on Earth. Some examples I'm sure you're very familiar are coal and crude petroleum. Okay, so in a barrel of crude oil, meaning it's not yet refined, here is what we can obtain. So we have gasoline, LPG, heavy fuel oil, jet fuel, other distillates, and diesel. Okay, so but we know that we should be turning away from fossil fuels because these are non-renewable energy and because um, it results to a net increase in the concentration of carbon dioxide in the atmosphere, which results to global warming. And it started during the industrial period, wherein the use of fossil fuels suddenly boomed, and they correlated the increasing CO2 concentration in the atmosphere with the anthropogenic or human-made emissions from fossil fuels. So next we have nuclear fission. Um, is a nuclear reaction where the nucleus of the atom is split into smaller parts, producing free neutrons and lighter nuclei. And as a result, it produces energy. So they say that it's also non-renewable because of the supply of the nuclear fuel. And we also have nuclear fusion. I think right now there's a big development in this technology. I think, um, but not enough so that it can be the mainstream source of energy. So, what is fusion? I'm sure you're also familiar. It's combining nuclei to produce larger atoms, and thus the result is a very large amount of thermal and radiant energy. And an example would be the fusion of hydrogen to form two hydrogen nuclei to form helium. And this is found, this reaction is found on the sun. We move on to the renewable energy sources. So we have solar, geothermal, wind, biomass, biogas, and hydroelectric, which are the um, preferred energy sources compared to fossil fuels. Of course, nuclear fusion and fission may also be considered as clean energy, but for nuclear fusion, um, uh, there are many risks, say the leakage of the radiation and dealing with the waste from the fusion. And then for fusion, it's not yet developed, it's still expensive. So that's why we look for others renewable sources or clean we look for other clean sources of energy like the solar energy, which I think would be one of the future. So right now it's popular as well, but I think this is the future. Solar energy, where we harness the radiant light and heat from the sun, um, can involve solar heating, solar photovoltaics, solar thermal electricity, solar architecture, and artificial photosynthesis. Okay, so this is a diagram of a photovoltaic solar power system. So we have the solar cells, inverter, transformer, and the power lines. So hopefully in the Philippines, we would increase the solar energy generation. So next we have wind energy. Here, the kinetic and dynamic pressure present in the wind is converted to electrical energy using a wind turbine and generator. But just like solar energy, its main disadvantage would be the geographical location. It's dependent on areas where the wind is just right, not too strong, not too weak. So there's an optimum wind um, speed required for wind energy. Okay, so we do have our own in the Philippines. I think it's somewhere in the north. So um, so some of the places here also use wind energy, and we hope to increase the production of wind energy. So we have geothermal energy, which is the energy extracted from the heat in the earth. Um, Conditions are favorable when tectonic plates collide by, or slide beneath one another, and the best example would be in the Pacific Ring of Fire. So in the Philippines is on that Pacific Ring of Fire. That's why we have many volcanoes, and we do have geothermal energy power plants in the Philippines. Um, we have one near Los Baños, which is the Mactan power plant. Okay. So next we have hydroelectric energy, water stored behind a dam to a given height and allowed to run off. So the dam, there are water turbines at the bottom of the dam which now produce the electricity. Okay. Mm, so this is a diagram of the hydroelectric energy. So we have there should be a certain height, and then the water would flow. There is a turbine and a generator at the bottom. Okay, next we also have tidal power. Tides are the movement of coastal waters caused by gravitational forces of the moon upon the earth, and they are designed to extract energy. Tidal power is designed to extract this energy. So if you're curious, it looks like this. Uh, so we have the tide coming in. There are turbines that produce the energy, or the tide coming out. So next we have biomass energy, and these are the energy obtained from plant, human, or animal derived organic matter. So um, all organic matter is known as biomass, and the energy released from biomass is called bioenergy or biomass energy. So, what are examples of biomass? Wood from trees, agricultural crops and agricultural waste, wood waste, and the burnt wood from forest fires, animal and animal droppings also. So this example of power plant using rice husk. What's the advantage of biomass energy compared to the other uh, or renewable energy sources? It's the only renewable energy source that can be converted to solid, liquid, and gas fuels. So we need, like in our cars, we use liquid fuels, right? So biomass can be converted to bioethanol or biodiesel. And it's considered the universal energy carrier. Right. But I would say that the future is not the future based on the conferences that I attended, the future is more on solar energy batteries and hydrogen fuel cells. Why? Because they are more efficient in converting the chemical into electricity, because there's no intermediate step. So in the traditional production of power from heat, um, okay, I had to pause because of Shopee delivery. As I was saying, the fuel cells and the batteries are more efficient because there's no intermediate step of converting the fuel to heat, then heat to electrical energy or electricity. In fuel cells and batteries, the conversion of electrochemical energy to electricity is direct, whereas in traditional um, production of power, so from the fuel, which is usually a carbon-based fuel, the fuel undergoes combustion first to produce the heat, and then the heat is then used to uh, produce electricity. And this intermediate step makes it less efficient. Okay. So in the Philippines, this is our energy mix from 2017 to 2022. And what can you observe? Our dependence on coal is increasing. Right? It has an increasing trend. Whereas the other renewable energy seems to stay constant. Right? But for the fossil fuels, it's increasing, which is a very sad fact that um but necessary evil because we are growing in terms of population, and of course we have um lifestyle we have improving lifestyles, so the demand is higher, so we had to import, or we had to use coal and uh gas. But I think it really would um depend on the policies being um, made by the government, because it's still possible to invest in renewable energy. It's just that I think there's something wrong with the policies being made. For example, um, in that energy mix, more about 50% is import, or about 50% of the energy mix is imported to the Philippines, or we buy from other countries. The other 50% we source locally. So it's called the indigenous energy. So we import coal and we import oil to support our energy demand. Um, but because we can only supply 50% um through our own oil, natural gas, which the malampaya comes from the malampaya. We also have locally produced coal, and then the rest from renewable energy. So it's quite sad that we have to import 50% of our energy. I hope that we would develop more technologies and more infrastructure to support our energy demand locally. And it really depends on strong policies, right? Strong policies by the government. Okay. So now we move on. So that's just the introduction part. We now move on to the lesson proper, which is on the production of power from heat. So a heat engine or heat engines are machines that operate in thermodynamic cycle and do a certain amount of net positive work. As a result of the heat transfer from a high temperature body to a low temperature body. Some examples of heat engines include steam power plant, Carnot engine, gas turbine, internal combustion engines, nuclear power plant, and fossil fuel power plant. So this is the basic representation of a heat engine. We have a high temperature reservoir and a low temperature reservoir. So the heat is pumped, or heat is absorbed from the high temperature reservoir to produce a certain amount of work, and then heat the heat is also rejected to the low temperature reservoir. What are the low temperature reservoir? It can be the surroundings, such as the lakes and streams. What can be the high temperature reservoir? So these are the boilers. Okay. So in a steam power plant, um, a large-scale heat engine in which the working fluid is in a steady state flow is successively flows through a pump, boiler, turbine, and condenser in a cyclic process. So these are the four basic parts of a steam power plant: pump, boiler, turbine, condenser. And heat is transferred across a physical boundary. Meaning, for example, in a coal-fired power plant, the combustion gases are separated from the steam by boiler tubes. What do I mean by that? So this is a diagram of a steam power plant. So maybe either from afar, say you're traveling on a highway, you see from afar there's the stack or the cooling tower, but more on the stack, you see like a white smoke coming out of a very tall building like this. So it must come from a power plant. Uh, so what is that smoke made of? From the boiler, so we have the fuels. So remember your ChE 32, we have fuel and then air. Combustion happens in the boiler. The combustion gases at the high, since after combustion the temperature increases, they heat the steam inside the boiler tubes. Okay, so that's what I mean by physical boundary. The heat is transferred across a physical boundary. The physical boundary is the boiler tubes, meaning the combustion gases do not come directly into contact with the steam or the water pump in the boiler tubes. So what happens to the combustion gases? They are released to the stack. Okay, this is called the stack. And then the water becomes superheated to steam, and now the steam drives the expands in the boiler. I mean, expands in the turbine, where the turbine drives the electric generator. So from the expansion of the turbine, it goes to the condenser. So the temperature is still high, quite high. Now in the condenser, the temperature of the flow of the fluid is or it's cooled, so the temperature is decreased using a cooling fluid coming from a cooling tower. Okay. Now it's a cycle because after that, after passing to the condenser, it's pumped back to the boiler and then again to the turbine. So the cycle, it becomes a cycle. Okay. So that's the basic structure of a steam power plant. Now, if we want to become or to use clean energy, what alternatives can we do, right, to replace this fuel? So usually before we use coal or we use natural gas, basically fossil fuels. So if we want to use clean energy, we can replace this with bioenergy, right? So bioenergy, and there's also a technology wherein mirrors are used to reflect solar energy to heat, okay, to heat the boiler. So those kinds of retrofitting of the power plant maybe would be cheaper. Okay, would be cheaper because we are not like replacing the entire power plant, but we just retrofitted to to accommodate a cleaner fuel. So that's one way if we still want to use our old power plants. Um, but we can also like when we put up new power plants, um, we can opt to put like um, a solar energy um, source or like hydroelectric and or wind depending on the location. Okay, now what is a Carnot engine? It's a heat engine operating in a completely reversible manner. It operates between two heat reservoirs such that all heat is absorbed is transferred to the constant temperature at the constant temperature of the hot reservoir, and all heat rejected is transferred at the constant temperature of the cold reservoir. So it consists of two reversible adiabatic and two reversible isothermal process. Let's see what it looks like. So this is a Carnot cycle. We have a high temperature reservoir, and here is our boiler. Heat is absorbed in at a constant temperature, TH. Okay. Next, it expands in a adiabatic and reversible turbine to do some work, and the temperature goes down from TH to TC. In the condenser, um, heat is rejected to the low temperature reservoir at constant temperature Tc. Then it's pumped back to its original state in a reversible and adiabatic pump. The temperature uh, increases from Tc to Th. So what does it look like on a TS diagram? So by the way, the TS diagram is your best friend in this topic. So you are expected to always draw a TS diagram. So practice drawing a TS diagram. It will guide you through the process of solving the problems in this topic. This is a Carnot cycle on this TS diagram. From point 1 to 2, this is the reversible isothermal. So by the way, all the steps in a Carnot cycle are reversible. So this is the isothermal absorption of heat in the boiler at constant temperature and pressure. Next, from 2 to 3, the reversible adiabatic expansion of a saturated vapor. So this is the saturated vapor line. This is the saturated liquid line. Inside the curve, you have the saturated um, fluid. Okay, a mix of um, saturated vapor and saturated vapor and saturated liquid. So inside the curve, remember that. Okay, so from point 2 to 3, it expands to, so this is a higher pressure compared to this one. It expands to uh, wherein T saturated equal to Tc. Okay. So from 3 to 4 is the isothermal heat rejection in the condenser. Um, but so remember, we're still inside the curve. This is wet steam, a combination of liquid and saturated liquid and vapor. The quality decreases, meaning we have more liquid. We're approaching the saturated liquid curve, but it does not condense completely. So we did not reach the saturated liquid curve, but it has more liquid compared to point 3. Next, the reversible adiabatic compression uh, back to its origin, which is starts as a saturated liquid. Okay, so saturated liquid from point 1 becomes saturated vapor, and then wet, steam 3 and 4. So this is the Carnot cycle. Okay. Um, what is the use of the Carnot cycle? Although it cannot be achieved in real life since it's an ideal process, it's a reversible process, it could serve as a standard for comparison of actual steam plants. Next is the thermal efficiency of a Carnot cycle. How do we compute its thermal efficiency? So the work net done by this cycle is equal to the heat absorbed minus the heat rejected. Okay? So the efficiency is now the work net divided by QH. So it can also be expressed this way. And we use the absolute value signs to make the equations independent of the sign conventions. And this is what we call uh, the efficiency of a Carnot cycle, which is the ideal cycle. It's the maximum efficiency that we can approach but never reach. Furthermore, we can like I said express it in terms of the temperature. If the temperature is in absolute scale, we can just simply use the temperature to compute for the Carnot efficiency. Okay? So no need to know the heat values. Now we move on to the Rankine cycle. So it's an alternative cycle that's taken as a standard for fossil fuel burning power plants because the Carnot cycle will cause severe practical difficulties when applied to actual power plants. Why? Turbines that take in saturated steam produce an exhaust with high liquid content, causing severe erosion problems. So remember, in the Carnot cycle, um, our turbine inlet, okay, okay, a turbine inlet is a saturated vapor. Okay, so that causes corrosion problems in the turbine. Next is a design of a pump that takes in a mixture of liquid and vapor. So remember in our Carnot cycle, the pump is look begins here. Okay, the pump is here, and there's no pump that can take a mixture of liquid and vapor. That would be very difficult to design. So what what happens? The Rankine cycle adjusts the Carnot cycle to consider this design limitations. Okay, so instead, in the boiler, the fluid is heated to its to superheated state. Okay, and then uh, the saturated liquid, I mean, in the condenser, it is it releases the fluid in its saturated liquid. Now, since it is now liquid, the pump can handle it. And even there's subcooling. There's subcooling means um, in our diagram, in the pump, it now exits the saturation curve. Subcooling, this is a subcooled region. Remember, this is the superheated region. So, um, in the TS diagram of a Rankine cycle, consists of the following steps. First, the constant pressure heating. So this is an isobar right here. Constant pressure heating in the boiler consists of three sections. As heating of subcooled, so subcooled we're outside the saturation curve. Heating of subcooled liquid to its saturation temperature. Here, why saturation? It touches now the saturation curve, right? So that's A. Vaporization at constant pressure and temperature. Vaporization from saturated liquid, it's transformed to saturated vapor. And then this part is superheating. Superheating of the vapor to a temperature well above its saturation temperature. Okay. Then from 2 to 3, this is the um, turbine. Okay, this is a turbine. There's a reversible adiabatic expansion of vapor in the turbine to the pressure of the condenser. And what do you notice? So initially in the Carnot, we're just operating in here in a square inside the saturated curve, right? But since there's superheating, now our outlet from the turbine is closer to the saturated vapor line, meaning there's less liquid and more vapor. And that helps with the design of the turbine that prevents the erosion problems. Okay, so it has more vapor. That's because it's further to the right compared to the Carnot, wherein it's further to the left. Now, the next step is the isothermal and isobaric cooling in the condenser. So from a wet steam, now it goes to the saturated liquids curve. So this purely saturated liquid, and the pump can now handle this purely saturated fluid, and it can begin its reversible adiabatic pumping to a subcooled liquid. So subcooled liquid outside the curve. Okay? And thus returning the cycle to its original state. However, the Rankine cycle still deals with reversible processes, yung step 2 to 3 and step 4 to 1. But in reality, okay, they it's not possible to have reversible steps. So power plants can build to operate that on a cycle that departs from the Rankine cycle because of the irreversibilities of the work producing and work requiring steps. Okay, I had to pause again because of food delivery. So as I was saying, um, the actual power plants that depart from the Rankine cycle can be built to consider the irreversibilities of the work producing, the turbine, and the work requiring steps, the pump. So remember in the TS diagram, completely vertical line means the entropy is zero, meaning it's reversible. But in reality, the flow should always lean to the right where entropy increases, symbolizing the irreversibility of the process. Okay. So lines 2 to 3 is actually not vertical, but tend to be in the direction of increasing them entropy. And then lines 4 to 1 also tends to lean to the right. Okay, so increasing entropy. The turbine exhaust is normally still wet because it's inside of the saturated curve. But as long as the moisture content is less than about 10%, okay, since we are far to the right rather than to the left or closer to the saturated vapor, which means that the quality is higher or the amount of vapor is higher, as long as the amount of liquid saturated liquid or the amount of moisture is less than 10%, then erosion problems are not serious. And also, um, slight subcooling of the condensate in the condenser may occur, but the effect is inconsequential. So this line might extend outside the saturating curve, but the consequence is inconsequential, but the effect is inconsequential. Now let's look at the energy balance. This is the energy balance equation for a steady state flow. So remember, we focus on the boiler, heat absorbed in the boiler. So boiler first. In the boiler, okay, we assume that the change in potential energy and change in kinetic energies are negligible. Okay, then there's no work produced in the boiler. So we're left with Q equal to change in enthalpy times the mass of the flowing stream. Um, in the same way, okay, that's the same thing that is happening in the condenser. We make the same assumptions and then there's no work in the condenser as well. So the equation for both boiler and condenser is this one. So remember this, okay? Now, for the turbine, again, we can assume these quantities to be negligible. And then in the turbine, we assume that um, it's adiabatic, okay? There's no heat flow. So we're left with the work shaft equal to the change in enthalpy times the mass of flowing stream. So please remember this value. I mean, this equation for the turbine. How about for the pump? Okay. So it's almost the same with the turbine. We make the same assumption about the potential and kinetic energies, and we assume an adiabatic process. Um, we're left with the same equation as the turbine. However, okay, the properties of compressed liquids are seldom available, meaning um, the properties of enthalpy, okay, for compressed liquids are not as available as the steam properties. So we can make use of the fundamental property relation, this equation, and if we assume constant entropy, okay, we're left with this equation, the integral of VdP from P1 to P2. And since V is independent of pressure for liquids, um, we're left with this equation, which we're in the ideal. So ideal delta H. Okay, so that's why there's a sub S here. It means this is the reversible constant entropy value is equal to V delta P. So why do we compute the reversible or the ideal delta H? We can just make use of the pump efficiencies later on to compute for the delta H actual. Okay. That's the next slide actually. So For the power plant that assumes negligible pump work, okay, so meaning we mainly rely on the turbine for the net work. Okay, so because there's negligible pump work, so it's the work produced by the power plant divided by the heat absorbed in the boiler. Since our equation for this is the turbine, okay, remember this is our equation for the turbine, this is the equation for the boiler. So substituting those equations into the efficiency equation, we're left with this equation for the efficiency of the power plant with negligible pump work. So we get this, either we compute these values or we values of enthalpy, or we get them from the steam table. Okay. Next is, what if the um efficiency, I mean the work of the pump is not negligible. So we have to consider that in the net work. So using the efficiency equation, our net work is the combined work of the turbine and the pump. But conventionally, okay, you'd know that this would have opposite signs because the turbine is um generating work and the pump is requiring work. However, it will be reflected later on the values of the enthalpies. That's why we just use plus here. So the enthalpies will ensure that the sign conventions are followed. Okay? So this is the equation for the turbine, work of the turbine, and this is the equation for the work required of the pump, and this is the equation for the boiler, Q sub H, or the heat absorbed in the boiler. We just simply substitute in the equation the mass of flowing stream. I forgot to tell you that the mass of flowing stream cancels out the previous slide, and the same way in this slide. So we're left with this equation for the efficiency of a power plant with non-negligible pump work. Okay. How about the efficiency of the turbine and pump? So the entire power plant has its own efficiency, but the turbine and pump would also have their own efficiencies. And it's computed by comparing its actual work generated for the turbine, which is the H3, okay, enthalpy at point 0.3 minus the enthalpy at point 0.2. That's the actual work produced by the turbine divided by its ideal work, or the isentropic work, which is H3 prime minus H2. Okay, so for the turbine and pump, it's always their actual work generated or required divided by their um isentropic or ideal work. So for the pump, okay, I'm sorry, I have to correct myself. So in the turbine, we are expecting that the work generated is always lower than the actual, I mean, the work generated is always lower than the ideal work. That's why the actual work is in the denominator. Okay, but for the pump, it's the opposite. The ideal work required is always lower than the actual work required. Okay? Because in the ideal world, okay, the pump would require less work. But in the actual world, okay, it will require more work or more electricity, right? So in the pump, the ideal work required is in the numerator. So remember that because efficiency is always less than 1. So the lower value should always be in the numerator. Hope that's clear. So for the pump, okay, we're comparing its isentropic work with its actual work required. So now we move on to an example problem. Okay, let's read it first. 500 psi A steam is superheated to 1000 degrees Fahrenheit before expanding through a 75% efficient turbine to 5 psi. No subcooling occurs and the pump work is negligible compared to the 200,000 kilowatt generator. Oh, it's weird. It makes the British units with the SI units. What quantity of steam is required? What is the heat ejected in the condenser? Okay, so I'm sharing the screen. You should be able to see next my whiteboard. Yeah. So hoping that you're seeing the whiteboard right now. Okay, let's um, begin solving the problem. Hold on first. Okay. So let's write the required. Oops. Bear with me. I'm not used to writing on my right pad again. Okay. Okay. Given pala, given. Given first. Given first. What am I doing? Yeah, given. So we're given, um, so the best way to write the given is to imagine it on a TS diagram. So let's draw a TS diagram. Can't make a straight line here. Okay. Let's draw a TS diagram. E S. This one looks like a positive sign. It's a Rankine cycle, okay, or a modified one because it's an actual cycle. So the conditions are, so steam is superheated. Steam is superheated to point 2, okay, and condenses and expand to point 3. So since this is an actual process, the expansion is actually that one. And then, okay, so after that, there's condensation. But the problem did say that there's no subcooling. No subcooling, so, and the pump work is negligible. So there's no subcooling. We don't exit the saturated curve. Okay. And then the cycle is brought back to its original. So let's label the points. We begin here in the boiler. This is point 1. And then this is point 2. This is 3 prime, the isentropic expansion. And this is the actual expansion, this point here. And this is point 4. So it's better to begin with that so that we know when we label our properties. Okay, we know their location on the TS diagram. So given at 500 psi superheated to 100 degrees Fahrenheit. So we know that this is an isobar right here. Okay, this is an isobar. So we know that P1 equal to P2, okay, equal to 500 psia, and then we know that it's superheated to T2 equal to 1000 degrees Fahrenheit. Okay. And then what else is given? Mm, its efficiency of turbine equal to 75%. 75%. Expanding to 5 psia. So we know that T P3 P3 prime P3 is 5 psia. Okay, what else? Negligible pump work. Work required by the pump is 0. Um, so the required value is quantity of steam. So the required would be the mass of flowing stream and also heat rejected in the condenser. So that would be our QH. So these are required. By the way, there's also a given um, the work of the turbine, 200,000 kilowatt. So the work shaft, so this is the work of the turbine, is 200,000 kilowatts. Okay? Next is, so let's begin at point 2. Okay, let's begin working at point 2. So at point 2, we know that we are on a superheated region. So we have the superheated steam, di ba, at point 2, where P2 equal to 500 psia and T, okay, psia and T equal to T2 is equal to 1000 degrees Fahrenheit, right? So hmm, from the steam table, we can read the properties of the superheated steam. Okay, so the properties, H2. So why do we need these prop H, and we remember the equation of the work for steam, diba? It's H3 minus H2 multiplied by the mass of flowing stream. So we want to know the mass of flowing stream. That's one of our required values. Okay. So we know that H at point 2, okay, we know at point 2 from the steam table, from ST diba? H2, read it using the pressure P2 and T2, it's 100, 1520.3, 1520.3 BTU, BTU per pound mass, BTU per pound mass. And then um, S2 is 1.7371 BTU per pound mass Rankine. Okay? So, next um, what can we do? So, we need the value of H3. Okay? However, uh, we don't have the details. We don't have like, we just know it's P3, but it's wet steam. So we need the quality to know the exact value of H3. And at the same time, um, we can make use of the fact that H3 prime is an H2 to H3 prime is an isentropic process. Okay, so our next goal is calculating H3 now. So once we calculate that, we can know the MFS because work shaft is given. So let's try to write the properties of H3 prime or at point 3 prime. Hmm. Okay, so now we're point 3 prime. So wet steam, we know it's wet steam, and we know that P3 is P3 P3 is 5 psia, and it's also equal to P3 prime. And we know automatically since it's saturated, we know it's T Y. So from the steam table, we can know this value, saturated properties from the steam table. Okay? Um so using the fact that this is an isentropic process right here. So hold on. Let me browse. Oops. So from H2 to H3 prime is an isentropic process. Okay. Therefore, H, I mean S3 prime, right, equal to the value here, right here, what we read from the steam table. I have not put the units anymore. And therefore, since we are dealing with the saturated properties, we can know the entropies of the liquid and vapor part. Okay. So S3L is 0.2349. S3B is 1.8443. Okay. Now, um, we can calculate now the quality of the steam, Okay, quality of steam at H3 prime. Okay, at H3 prime. So let's do that. So you remember how to do that using the entropy, diba? So we have S3 prime. Hmm, S3 prime equal to S3L times 1 minus X prime. Okay, so we're dealing with the quality at the isentropic expansion plus S3V multiplied by X prime. So just substitute the values of S3 prime, S3L, solve for X prime. Okay, X prime is 0.9334. That's the quality at H3 prime. So using that, we can calculate for H3 prime. Okay? Because H3 prime just H3L times 1 minus X prime plus H3V times X prime, right? And do we know the values of H3L and H3V? Yes, because we know P3, it's a saturation curve. Inside the saturation curve, we know P3. Okay, so we can read it from the steam table. From the steam table, H3L is 130.3 and H3V is 1131.1. So plugging those values into the equation here would give us H3 prime, which is 1064.44 BTU per pound mass. Okay? So that's H3 prime. Um, so now that we have H3 prime, what would be our next step? We can calculate for the work ideal. Okay. So remember, work ideal, what's the equation for a turbine? So this is the work ideal equal to delta H S times mass of flowing stream. But we know that delta HS is just H3 prime minus H2, right? Kasi it's the isentropic expansion. Balikan natin to. Okay. It's the isentropic expansion from H2 to H3 prime. So delta H isentropic is H3 prime minus H2. Mm. Okay, next is we solve for delta H S. So we substitute the values H3 prime and H2. Oops. We substitute the values. That would be 1064.44 minus H2 sa taas. Diba? It's 1520.3. So delta HS is negative 455.8599. So the negative sign, it means the work is done by the system. Okay, so now that we have the ideal ideal delta HS, we can use it to calculate for the